in this video we're gonna start learning about series. To define series, we need sequences because we have a sequence, a sub n, and we're gonna call the series to another sequence we name s of n, where s of n is defined as the sum from I equals to 1 to n of the elements a sub I of this sequence we had. So s of n is the nth partial sum. When the limit of this new sequence s of n exists, we say that this series is convergent and that L is the sum. You can also find this as summable instead of convergent, but in this video series we're gonna call it convergent. And if the limit doesn't exist, then the series is called divergent. So as always, let's start with a few examples. For the first example, let's take the sequence a sub n to be n. So a sub n is the sequence 1, 2, 3, and so on, all the natural numbers. And what we're going to do is create this other sequence. So s of n is going to be the sum from I equals to 1 to n of a sub I. So then S1 is going to be the first element, 1. S2 is going to be the sum of the first element and the second one. S of 3 is going to be 1 plus 2 plus 3 and so on. S of n is 1 plus 2 plus n. So what we want to find is the limit when n tends to infinity of s of n, and that is the limit when n tends to infinity of the sum from I equals to 1 to n of a sub I. As we've seen in videos in the Algebra 1 series, this sum is n times n plus 1 divided by 2. So what we're trying to do is find the limit when n tends to infinity of s of n, which is n times n plus 1 divided by 2. And we know using things we learned with the sequences that this limit is infinite. So then s of n diverges. And now for the second example we're going to show a very well-known series. This time the sequence a sub n we are given is 1 over n factorial. And we're going to call e sub n to the partial sum from I equals 1 to n of a sub n. That is the sum from I equals 1 to n of 1 over I factorial. And this series has a very well-known limit, and the limit is the number we've talked about in previous videos called e. And the way we're gonna write this is saying that the sum from n equals 1 to infinity, this is like taking the limit of the partial sum e sub n, so this sum of 1 over n factorial equals to e. To explain this, let's start by calculating the first terms in the series, that is e1 equals to the sum from I equals 0 to 1 of 1 over I factorial. This is when I equals 0 we have 1 over 0 factorial plus when y equals 1, 1 over 1 factorial. 0 factorial is 1, so then we get 1 plus 1, which equals to 2. Now the second element will be the sum from I equals 0 to 2 of 1 over I factorial. And this is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. And this is 2.5. The third element is the sum from I equals 0 to 3, 1 over I factorial. So we have 2.5 up to 2 factorial plus 1 over 3 factorial. 3 factorial is 1 over 6. And something important to notice here is that 1 over 6 is smaller to 1 over 4. So this is smaller than 2.5 plus 1 over 2 squared. And with this, what we get is that this first element is smaller to 3. This one is also smaller to 3. This one, again, smaller to 3. And in general, what we're going to have is that E sub n can be written as the sum from I equals 0 to n of 1 over I factorial. And this is 1 plus the sum from I equals 1 up to n, because the element when I equals 0 equals to 1 of 1 over I factorial. And this is smaller than 1 plus the sum from I equals 0 up to n of 1 over 2 to the power I. And this number is also smaller to 3. So our sequence E sub n is bounded because its elements E sub 1, E sub 2, E sub 3, and so on, E sub n, are always smaller to 3. Another important thing to notice is that E sub n is the sum of 1 over I factorial. And 1 over I factorial is always greater than or equal to 0. So E sub n is monotonically increasing. If you don't remember what this meant, then I recommend you go check out the videos about sequences. So E sub n is a bounded and monotonically increasing sequence. And this, with a theorem we had, tells us that E sub n converges. And it's actually a very complicated calculation, so we're not gonna do it, but it converges to E, where E is the number 2.71. It's an irrational number. So now let's talk a bit about conversions. We have a sequence, E sub n. We studied whether this sequence could converge or not, but now we don't care much about that. We only care about making the sequence a series. And we don't yet know how to study series, but what we do know is that we can call S of n to the partial sum of the elements in my sequence, and then this is also a sequence. And we already know how to study sequences, so we're going to use all those tools to study S of n. And we already have a definition for when a sequence converges. So we can now transform that definition into this other sequence. And then we'll have the definition for when a series converges. So the definition was that for every epsilon greater than 0, there exists a number n, natural, such that my sequence, in this case S of n, minus my limit, is smaller to epsilon for every natural number n that's greater than or equal to this n I found. And what is S of n? Well, S of n is the sum from I equals 1 to n of a's of I minus L. And as I said, we know things about sequences. We know that in sequences, a sequence was Cauchy if and only if it converges. And what does Cauchy means? Well, that for every epsilon greater than 0, there exists a number n natural such that S of n minus S of m is smaller to epsilon for every n and m greater than or equal to n. So what we did is we just replaced the things we had for sequences, the a's of n and the a's of m we had for our new sequence s of n. And now s of n and s of m are the sum from I equals 1 to n of a's of I minus the sum from I equals 1 to m of a's of I. So let's think for a minute about these two sums. We have a's of 1, a's of 2, and so on, a's of m. And then we have a's of m plus 1, and so on, a's of n. What we're doing is, this sum is adding all these numbers up from a1 to am. This is the sum up to m of a's of I. And then this other sum is taking again all these elements, but up to n. So when we subtract the pink section to the blue one, we have to remove all these elements. And so the only ones we're adding up here are these ones. So the green one is the sum of a's of I from I equals n plus 1 to n. And that is what being Cauchy means. It's that the sum from I equals n plus 1 to n of a's of I is smaller to epsilon for every m and n greater than or equal to n. And so using all these definitions, we have this corollary that says that if the series with the absolute value of a's of n converges, then the series without the absolute value has to converge too. And another corollary is the test of the nth element. It says that if a sequence a's of n does not have limit 0, then the series formed by this sequence diverges. Notice that this is very different than saying that if a's of n has limit 0, then the series converges. This is not what this corollary is saying, and in general is not even true. A good example for this is the sequence a's of n equal to 1 over n. A's of n has limit 0, but as we'll see in other videos, the sum of a's of n, that is the sum of 1 over n, diverges. So now if we go back and remember about what we did with the series that converged to E, then we can have this theorem. If we have a sequence that's positive, then the sum will converge if and only if it is bounded. The proof for this is actually what we did before, so I'm not going to do it in this video. But the idea is that if all the numbers in the sequence are positive, then S of n is monotonically increasing. Another very important theorem is called the comparison test. We have two sequences, both greater than 0 and a of n greater to b of n. When the series of the greatest element converges, the series with the smallest element will converge. And when the series with the smallest sequence diverges, so does the series with the greatest elements. Intuitively, it does make sense, but let's go ahead and prove it. Let's call this one number 1 and number 2. So we have that the sum from n equals 1 to infinity of a of n, that is, the series converges. And now going back and look at this theorem we have that if a sum converges, then the sequence S of n is bounded. So what we're going to do is call this sequence A sub n of partial sums. So as the series converges, this sequence is bounded. Then there exists L such that A sub n is smaller than or equal to L. Now, because of our hypothesis, we have this. So B sub n is smaller than or equal to A sub n. And this happens for every n. So the sum of the elements of B sub n will be smaller than or equal to the sum of those in A sub n. And so this is the partial sum B sub n is smaller than or equal to the partial sum A sub n. And we said that A sub n was smaller than or equal to L. So then B sub n is also smaller than or equal to L. That is, B sub n is bounded. We also have that 0 is smaller than or equal to B sub n. And then our series B sub n, the partial sums, will be monotonically increasing. And again, using this theorem, we have that's monotonically increasing and that it's bounded, and so it converges. And when the sequence of partial sums converges, so does this series. And now the proof for the second one is going to be left as an exercise because it's very similar to the first one. Remember that if you follow me on Patreon, you have access to this type of exercises solved.